Okay, Assalamualaikum and very good morning. Okay, so welcome to our lecture session. Okay, so today we cover to we go for the second chapter. And the first chapter we look at for the basic components of vibration, what is the elements vibration, how to define the equivalence for the spring stiffness, the damping, and the mass. Okay, and then how we define the degree of freedoms. That's for the first chapter. Now second chapter we go for the how we analyze the vibration system lah. For this subject, okay, basically for the first half of the semester we look at for the first degree of a single degree of freedoms. Okay, so which is you can divide it by two chapters lah. So which is chapter 2 for the undamped system and chapter 3 the damped vibration system. Okay, and part 1 today we cover for the part 1, so which is we are looking for the free vibration. So free vibration is meaning that the vibration is only vibrate by its own when you give the initial conditions without any external force lah. So basically it's a self oscillation lah. Oh, sorry. This one for last semester. Okay, so the outcomes for this chapter, which is so that we are able to develop the equation of motion for undamped single degree of freedom, translation, and rotational system. Okay, so which is you are given a system and then how to identify all the applied forces when there is a motion of the object. And then analyze the total response of undamped single degree of freedom, translation and rotational. So which is the response here is referred to the motion of the subject. Okay, single degree of freedoms is the simplest form to represent system or structure. So which is actually even the complex model we can simplify as a single degree of freedoms to which is to find the easy solution. Oops, okay, as an example, this one is the tower. Okay, so if we are interested to study the motion of this tower in the horizontal directions, actually we can model as a single degree of freedoms. Okay, so which is the mass on top of the tower we can consider as the equivalent mass. Okay, and then the support tower itself we can consider can model as a cantilever beams. Okay, so which is calculate the stiffness and then we can model as a single degree of freedoms. Okay, so that's how we model the system to study the dynamics or the motion of it. Okay, so this one is the simplest. We model as a spring mass system and them lah. So which is a spring and mass system. So that's the example how we model the single degree of freedom. Okay, so now and there is a single degree of freedom, free vibrations. So free vibrations meaning that there is no external force induced to the system. Okay. So basically for the spring mass system, okay, so if there is a motion of for the mass, so for this case we assume that the mass move in the downward directions as a positive displacement, and at the same time the acceleration also move the same direction, okay, so goes to the downward. Okay, and now we are interested to look the means the reaction force from this motion. Okay, so for this case, this is a spring and mass system. Okay, so if the spring is a relative to the displacement, so if there is displacement, meaning that there is a reaction force from the spring. And then the mass have the inertia. So if there is accelerations or the change of velocity, there will be the force, the inertial force induced to the system. So now we look at for the, we assume that the system in the dynamics equilibriums. Okay, so the dynamic equilibriums, so which is total force equivalence to zero. So under this relationship, so if the mass move to the downward directions and the spring in the compressions, okay, compression state, so mean that the reaction force we push to the upward direction. Okay, so the magnitude of the force is depend on how much displacement for the spring. Okay, so for this case, the displacement of the spring is equivalent to x. So x is meaning that the displacement for the spring. Okay, so kx. So the direction is in the upward directions. Okay, so now we look at for the inertia. Okay, so the inertia, you have to know the inertia is it always goes to the opposite directions of the motion. So now the mass move to the downward direction, and the initial reaction from the inertia will goes to the opposite direction. So now the mass move downward, so mean that the initial force will goes to the upward directions. Okay, so which is the magnitude is m x double prime. Okay, so mass times by accelerations. Okay, F equal to ma. Okay, so now based on the force equilibriums, okay, so which is total force equal to zero, so we just have to summation to get the equation of motion. So kx plus mx double prime equal to zero. So that's the equation of motion for this system lah. Okay, so that's the way we draw the we derive the equation of motion and also draw the free body diagrams. Okay, so if you're going to draw the free body diagrams, make sure that you state you state all the forces applied in, which is you have to consider the magnitude, for this case the magnitude kx and mx, and also the directions, okay, either upward or downward. So all must be clear lah. Okay, so this is the equation of motion, so which is from that we can derive the motion, which is what we interested. We want to solve this value. Okay, so the x value. Okay, so x is we call as the response. Okay, so the response, the motion. Okay, so this is the vibration response for the single degree of freedom. You know that when the single degree of freedom spring mass system, when you give an initial condition and then you release, it will oscillate. So which is it move up and down. Okay, so the motion of the mass we can represent it in the sinusoidal function. Okay, so which is the motion has the amplitude, okay, and the frequency. Okay, so the amplitude is represent that how much the displacement, okay, and then the frequency is related to how fast it move. So we see how fast it move, which is how many oscillation within 1 second. So that's related with the frequency. Okay, so which is this sinusoidal functions we can represent into mathematical equation. X is equal to a sine omega t plus beta. Okay, so which is a is the maximum amplitude. Omega here is referred to the frequency. Okay, frequency in radians over seconds. Okay, so to calculate frequency from the graph. So you can measure the period of oscillation. So which is the time taken for the one complete oscillations. For example, this one we start from 0 and end at 0 lah. So which is one complete oscillations. So the times taken. So which is we call as a period of oscillation lah, T. Okay, and then to convert into radian over second is equivalent to 2 pi T lah. Because one complete oscillation is equivalent to 2 pi radians. And B is a phase angle lah, beta here, beta is phase angle. So phase angle actually is referred to the where it started lah. So the starting point, the angle at the when T is equal to 0. Okay, so the displacement we can represent as a x lah. So which is we can call as a x equal to a sine omega t plus beta. Okay, so the velocity is the derivation lah. Okay, so which is we differentiate the displacement to get the velocity. Okay, so we can use symbol x dot lah. Same goes for the acceleration. Okay, so we differentiate sine, we got cos. Okay, and then differentiate the value inside sine, we got omega lah. So a omega cos omega t plus b. Okay. And here is the accelerations. Acceleration is we differentiate the velocity. Okay, so cos differentiate, we got minus sine. Okay, then this one omega, so minus a omega square. So this value is referred to the x max, the maximum amplitude. Okay, so this value, the value in front of cos, we can consider as a x dot max, and then this value is referred to the x double prime max. We can simplify it to minus omega square x. So because a sine omega t plus b, we can substitute as a x. Okay, so we just separate minus omega square. So minus omega square x for the acceleration. Okay, so from the previous derivations, so total force is equal to 0. Okay, and then I found that the mx double prime plus kx equal to 0. So which is x double prime can be represented as a minus omega square x. Okay, and then substitute in these equations. Then we got this relationship lah. So okay, this one we can define the value for the omega. So omega is equivalent to square root of k over m. Okay. So which is there is two forces which is always acting on the mass for the spring mass system. Stiffness force. Okay, so stiffness force is a kx. So which is you can define as words to bring mass back to the position of equilibrium. This force constant with respect to the frequency. So which is this force doesn't affected by frequency. No matter how fast you the motion of the mass doesn't affected by frequency lah. So keep constant lah, the value. Just depend on the displacement. And initial force. Okay, so initial force is we can represent as a mx double prime lah. So mx double prime, or we can represent as a mx omega square. Okay, so which is initial force. Okay, so which is worth to eliminate the acceleration of the mass lah. So which is to counterbalance lah. So this one is this force function of frequency lah. So meaning that the value For the inertia, is depend on the motion of the mass. So higher frequency can have the higher inertia force. Okay, so now we look at how to study the motions, which is the vibration response with initial conditions. Okay, so we know that for the spring mass system, that system will not oscillate if you didn't give the initial conditions. Okay, so to make it motion, you must give initial condition. So initial condition means that you give the initial displacement or initial velocity or both of them. Okay, so that's why for the free vibration, we only give the initial condition, and then we let it self oscillation. So as you have a spring mass system, okay, so this system have a spring, you press and then you release, then start oscillate. So that's the meaning of free vibrations. Okay, so the initial condition is how you induce initial condition to make it oscillate lah. So we call also known as a initial disturbance. The same the same terms. Okay. So the equation of motion spring mass system in the vertical can be represented into this form. Actually, this one is the same sinusoidal function. Okay. Okay, A sine omega t plus beta, the same equation, which is equivalence. Okay. This form or this form, the same form actually. Okay. So the first equation, it have the phase angle. Okay, but this equation doesn't have the phase angle, but it have sine and cos at the same time. But in actual, it still represent the same equation if you plot. Okay, so this one actually is equivalence to A sine omega n t plus beta. Just equivalence. So which is here A equal to the square root of A1 square plus A2 square. Okay, and then beta is the inverse of the tangent A1 over A2. Okay, so that's the relationship. So you can write either this form or this form. But in this case, to make it easier to solve, we convert this form into this form. Okay, so which is A1 and A2 so it's easier to solve because we want to find that what is the initial when we induce initial condition, which is initial displacement and initial velocity, and what happened to the vibration response. Okay, so this is the displacement. Okay, and then we can differentiate this equation to get the velocity so the velocity is x dot, which is equal to, so we differentiate cos, we got minus sine so minus a1 a1 omega sine omega nt plus a2 omega n cos omega n t. Okay, so this is the velocity equation for the single degree of freedom system, spring mass system, single degree of freedom. Okay, so now we want to, because the motion we already know, when you give the initial conditions, that's the motion. Okay, but we have to complete the equation, because we want to know what is the amplitude, what is the frequency, and what is the phase angle. Okay. So we know that the frequency is depend on the stiffness and the mass of the system lah. That's how we calculate the frequency. So now we want to calculate the response, how is vibrate, what is the amplitude, and what is the phase angle. Okay, so now we want, you must know that the initial condition, because without initial condition, this system will be not oscillate lah. But after you give initial condition, it will oscillate. Okay, so initial condition, which is when t equal to 0 lah. So when t equal to 0, okay, so which is we have initial displacement and initial velocity. Okay, so when t is equal to 0, the displacement we call as a x naught lah. So x naught can be represented as a initial displacement. Okay, so x naught here. So now when t is equal to 0, okay, so t equal to 0, cos 0 equal to 1. So a1 plus sine 0 equal to 0 lah. So a1 lah. So that's why x not equal to a1. So x not, x when t equal to 0, displacement is equal to a1. So which is equal to x naught. Okay. So in this case, a1 is equal to x naught lah. Okay. And then initial velocity. Okay, so initial velocity when t is equal to 0, we substitute t equal to 0 for this equation. Okay, so sine 0 is equal to 0 lah. So this one can just slash. Okay, a omega n cos omega nt. Okay, so cos omega nt when t equal to 0, cos 0 is equal to 1. So a to omega n. Okay, so which is a to omega n is equal to s dot naught. So this is how we can get this equation lah. So now we can complete these equations. So a1 equal to x naught and a2 is equivalent to x naught over omega n lah. So from this relationship lah. And then this is the general solution lah. The general solutions for the free vibration single degree of freedom. Okay, so which is xt is equal to x dot cos omega nt plus x dot naught over omega n sin omega nt lah. So this is the solution lah for the single degree of freedom. Or we can represent into this form if you want to calculate the maximum displacement A. So this equation actually is still sinusoidal, but you cannot straight away, it's not easy to interpret lah. So that's why to interpret, better convert into this form lah. To convert into this form, which is the maximum amplitude A is equal to the square root of x naught square plus ni lah, a1 square plus a2 square lah. Same goes for the beta lah. So beta, which is inverse tangent of a1 over a2. So basically, this value we define the maximum amplitude lah and the phase angle. The frequency doesn't change. So if you give the difference initial condition, it's only change the amplitude of oscillation. It doesn't change the frequency because the frequency is totally depend on the stiffness and the mass of the system. So meaning that if you give the low initial conditions, example, if you will vibrate like this, okay. If you give the higher initial condition, higher initial displacement, so the response will be like this. Okay. Time, amplitude. Okay. So this one, low, it's not. This one, high, I x naught. Okay, so which is the initial condition doesn't change the frequency. Okay, so it's only change the amplitude of the vibration. So you give the higher initial displacement, you will get the higher amplitude of the vibrations. But the times taken to complete one oscillation is remain same. It doesn't change the frequency because the frequency is depend to the stiffness and mass doesn't depend on the initial condition. That's the thing that you have to understand lah, about the motion of a system, single degree of freedom. Okay, so this is graphic representation lah. So the phase angle. Okay, so actually the sine and cos is almost same lah. You can use the sine function or cos function. So cos is a sine function plus 90 degree lah. But if you are using the cos function, so basically if I start before the sine, so you must use minus lah. For the sine function we use plus for the beta. This one for the cos function lah, in case you because sometimes the question given in the sine or cos actually it's same the same function. The response still is goes up and down. Sine and cos remain the same function. It's just the phase difference of the 90 degrees. Okay, so we're looking for the exercise. Determines the maximum displacement, velocity and accelerations of the undamped mass spring system, which is K is given 500 Newton per meter, mass 2 kg, and with the initial condition of 0.1 and 5 meter over seconds. Okay, so basically for free vibration, to find the amplitude, the most important parameter is the initial condition lah. So with the initial condition, you cannot calculate lah what is the displacement value. Okay, the maximum displacement, the maximum velocity is incomplete. Okay, so now we want to find the maximum displacement. Okay, so maximum displacement is equivalence to A. Okay, which is the maximum velocity here is if you refer to the velocity equation is A omega n, and maximum acceleration here is referred to the A omega n square. Okay, so that's the value we want to calculate. Okay, so which is to calculate maximum amplitude. We need the information of initial displacement, initial conditions, initial displacement, and initial velocity. Okay, so initial velocity, we need the information of the frequency. Okay, so which is omega n. So omega n can still calculate based on the equation square root k over m. Okay. Okay, so now we want to calculate the A lah. Okay, so you can refer this equation lah. Okay, so this equation. So the general solution under initial condition. Okay, so A here is equal to the square root of x naught square plus x dot not over omega n, this one square. Okay, so s naught and s dot naught is the given in the question. Omega n still not given. Okay, so we have to calculate omega n. Okay, so omega n is equal to square root k over m. Okay, so which is k is given as 500. So please beware with the units. So make sure units, all the unit in the SI units, Newton over meter. So it's okay. You can just straight away using the the value, and mass is 2 kg. Okay. Okay, so this one we get 15.81 radians over second. Okay, so that we already calculate the natural frequency of the system. Okay, so now we can solve lah for the A. Okay, so X naught is given, which is 0.1 plus, okay, X dot naught is 5 over 15.81 square. So, which is equivalent to 0.331. So, the unit should be a meter lah. Okay, and then this is X-mat lah. Okay. So now we want to calculate the maximum velocity. Okay. So X dot max equivalence to A omega n lah. So which is A 0.331 times by 15.1. So this one you will get 5.244 meter over second. Okay, then maximum accelerations. Okay, acceleration, this one actually there is a lot of student in the previous semester. Okay, so because by refer to this relationship for the accelerations, so the question asks you the maximum accelerations. Okay, but this is common mistake by student. Student include the minus sign here. Okay, so the minus sign actually just refer to the phase angle. Okay, so the phase angle, so meaning that is sinusoidal function, but it goes to the opposite direction of you know. So but the maximum we still take this one is a maximum lah. So this one is still X max. Okay. So the maximum acceleration, you just take it as a omega n square. So please just ignore the negative sign. Negative sign just show the it move in the 180 degree out of phase as compared to the displacement. Okay, so please just take the value of A omega square. So just ignore the minus sign. Okay, so which is A omega n square. So 0.331 times by 15.81 square. So equal to okay, so that's the solution. Okay, so now we looking for another example. A helical spring, when fixed at one end and loaded at the other, require the force of 100 newtons to produce elongation of 10 mm. Okay, at the end of the spring, and now rigidly fixed one end vertical above other lah. Okay, and the mass of 10 kg is attached in the middle of a point of its line. Determine the times taken to complete one vibration cycles when the mass is set vibrating in vertical direction. Okay, so So the information given, the elongation of the spring when 100 Newton force applied to the spring. So actually these conditions uh, given to calculate the stiffness of the spring lah. Okay. So the solution, but the question asked to find the times taken for the one complete cycle. Okay, so which is we want to measure the period of oscillations. Okay, so the which is relates to the frequency of oscillation. So if you want to know that the period of oscillations, okay, so it's related to the frequency. So which is the frequency is depend on the stiffness, the value of the stiffness, and the value of the mass. So you have to know both of the value lah to find the period of oscillation. So now the first step we have to calculate the stiffness. Okay, so K here, K which is when the 100 Newton force apply have a 10 mm oscillation. Okay, sorry, displacement. Okay, so which are elongation lah. Okay, so the stiffness K is equivalent to force over displacement 100 over 10 mm. You have to convert unit of meter lah. So which is equivalent to 10 kilonewton over meter. Okay, so for this case, this is when the system will develop. So which is the mass of 10 kg attached to the stiffness with equivalent stiffness of 2K on the both side. Okay, so for this case, we have to know the arrangement lah. So the arrangement, okay, so bottom and upper spring, both of the spring is directly contact to the mass. So which is we can define as the parallel arrangement. So the parallel arrangement K equivalent is the summation of all the springs. So 2K plus K equivalents to 4K. Okay. Okay, so now we calculate the frequency of oscillation because we want to determine the period of oscillation. So omega n for this system, the frequency of this system is equivalent to square root K over m lah. So K is equivalent to 4K over m. So 4 times by 10,000 over 10 lah. So 63.2456 radian over seconds. Okay, so now we can after we know the frequency oscillation, we can find determines the period of oscillation. Okay, so omega is equal to pi f or 2 pi over t. Okay, so t is equivalent to 2 pi over omega, 2 pi divided by the frequency of oscillation, so which is equivalent to 0.0993 seconds. Okay, so which is a time taken for the one complete oscillation and move upward, downward, and back to the initial position, equilibrium position, is equivalent to 0.0993 seconds. Okay, another example, the maximum velocity attained by the mass of simple harmonic oscillator is 10 cm over second. The period of oscillation is 2 seconds. The mass is released with initial displacement of 2 cm. Determine the amplitude, the phase angle, and the initial velocity, initial accelerations. Okay, so this one just want to test you how to manipulate the parameters to get all the value. Okay, so we know that the motion A sine omega nt plus theta or beta beta. So for this case, we use a beta as a theta here. So the amplitude A is depend on the initial displacement. Okay. But initial displacement, you have it's only given the initial displacement, but no information about initial velocity, so which is the thing that you have to calculate and the maximum acceleration. Okay, so based on the information given. Okay, so maximum velocity is given. Okay, the period oscillation is given. Okay, so which is period oscillation given, so meaning that you can get the natural frequency. So maximum frequency is given. From that you can estimate the amplitude lah, because maximum velocity is equivalent to a omega n. Okay, so omega n you can get from this information lah. Okay, so t is equal to 2 seconds, and then from that you can calculate the omega n, so which is equivalent to 3.14 or equivalent to pi radians, pi radian over seconds. So this is the x, x naught and x double naught. X double dot. Okay. Okay, so now based on this relationship, we know that the maximum velocity is equivalent 10 cm over seconds. In the first place, you have to convert into SI units. Okay, so maximum velocity is equivalent to a omega n. Okay, so which is 0.1. So from that, we already calculate the omega n. So we can solve for the maximum amplitude. Okay, and then a naught equivalence to the given as 2 cm initial displacement. So t is equal to 0. Okay. So this one x0 is equal to a sine theta lah. Okay, so which is equivalent to 0.02 initial displacement after you convert into SI units. Okay, and then A we have already calculated. Okay, so now we can solve for the theta lah. So theta is inverse of inverse sine of the 0.02 over 0.03183 lah. So which is equivalent to 51.07 degrees lah. So now we have complete all the information, and then can solve lah for the initial velocity. Okay, so initial velocity is when t is equal to 0 lah. So based on these equations, we already calculate a omega n theta here. So we just substitute when t is equal to 0. Okay, so just put all the value, then you can estimate the initial velocity, and then the maximum accelerations equivalence to a omega n square. We already know the value of a and omega n, so it's not problem lah. Just insert the value and we can get the solution. Okay, any questions so far before we go for the another system? So first we go for the translation motion. So until this point. Next we continue with the torsional motion. Any questions so far? If no, if no question, we take a break around 5 minutes and we continue after this. Okay.
Okay.